Hello and welcome to another in my series of videos on control systems engineering. My name is Frank Owen, PolyX Engineering, San Luis Obispo, California. In this video we're going to look at a way to classify control systems that's somewhat convenient, and actually I have not seen this system used in the English-speaking world and was introduced to it as a guest professor lecturing in Germany. One day, a student came when I was teaching at the teaching controls at the Hochschule München, which is the Munich University of Applied Science. A student gave me this chart, and I'd never seen this chart before, and I'd taught controls for quite some time before that. So it was a new thing for me to see this method for classifying control systems. So I'm going to explain this chart for the benefit of control students in the English-speaking world, as well as for those students in the German-speaking world. The system's dynamic behavior, of any system's dynamic behavior, is encapsulated in its ordinary differential equation, the ODE. And I have an example of an ODE, a very generic ODE, written out here with the left-hand side being the system part of the equation, and the right-hand side containing the inputs. There's an input into the system. So the system, which is on the left, as I said, is forced by the inputs that are put on the right-hand side of the equation. Notice on the left-hand side of the equation we have, let's see, I'm going to click this a little bit. Yeah, this is the dynamic or the system part of the equation, and x in this equation is the variable of interest. So actually what we want when we analyze a system is we want x as a function of t, of time. We want the time history of x. That's the motion of the system, basically. The right-hand side of the system has u as an input, but notice that the u can be differentiated also multiple times, in this case m times on the right hand side. So basically the input is put in u and then it is pre-processed with these various operations being done to it, and then fed into the dynamic system, and the dynamic system responds or moves. We have an nth order system because there are n orders of differentiation here. And we have on the right hand side the input is differentiated m times. Of course, since this is a dynamic system, we're differentiating with respect to time, which is what you do for dynamic systems. Another way to look at this is graphically. We're going to change the variable names in a minute. We put in our input over here. This is the u that was in the previous equation. We're going to call it xi, I for input. We pre-process it, and basically what that means is we feed it through a controller, and then we send a signal out from the controller, from the pre-processed input that goes into the actuator and the plant, and then the system responds. So we will replace u with xi, which is input, and we will replace x with xo, and the O stands for output. Let's look at the pre-processing of the input signal, and basically this system, or this series of videos concerns PID controllers. There's a separate video on PID controllers, and then PID controllers are talked about all through the controller part of this series. The most common controller in use in industry is a PID controller. So basically we're going to put our input in, and then it's going to be pre-processed by this PID controller. And you can read more about the PID controller in other videos, but let me be brief here. Basically we have three paths in the PID controller. In this first path we feed the input in, we multiply it by a constant. This is called the proportional gain. And then we have a contribution to the final control signal that is proportional to the input. So this is the proportional action of the controller. Here, what we do is we take the input and we integrate it. 1 over s is the Laplace transform version of the integral. So we take the input, we integrate it, so we're getting the area under this curve, basically the area under this curve. And then we multiply that by this integral gain, which is part of the controller, and we have the integral action or the integral contribution of the control action. With the third part, we take the input and we differentiate it. S is the Laplace transform version of differentiation. And then we multiply it by the derivative gain of the controller, and we get the derivative action or the derivative contribution of the controller. And then we sum all those together, so the total control action is the sum of those three actions. Again, I'm not going to go into detail about the PID controller or why we use this algorithm. There's a good video on that introduces PID controllers and tells where the algorithm came from, so you're welcome to watch that video. And I've already said this, the output signals fed, it's these three actions, proportional, integral, and derivative, are added together and fed downstream to the actuator and then on to the plant through the actuator. So we're going to change this system a little bit. We're going to take the pre-processing part, which we just talked about, and replace these u's with xi's. And actually what happens here is you can see the lowest order of differentiation is actually integration. If this is the first order derivative and this is the 0th order derivative, and this is the the first minus 1 derivative. And basically what you can see here is that u is equal to the integral of the input. So we go back to the equation that we originally started with, our ODE, and we're going to replace our variables so that they're more in line with what we're doing with the control system. X becomes X0, where O stands for output, and the convention is to let the coefficient of XO, so that's right here, the 0th derivative of XO, be 1. So if we don't have 1 here, we will divide this entire equation by whatever that coefficient is, and then we will have this normalized form that we'll use here. And then we redefine the left-hand side coefficients to accommodate that fact. We use t for these coefficients, and we'll see that there's actually some significance to that. On the right-hand side of the equation, we see that we have, as we did before, the three gains of the PID controller times their corresponding derivatives or integrals of xi, the input. Now we're going to talk about the naming convention a little bit. The right-hand side of the equation, as we'll see here, as we've seen here, has all three gains. So this is a generic complete form. And if we had a situation like this where we had all three, then we would designate that as PID. On the left-hand side of the equation, we see that we have the nth order derivative of XO, and we indicate that by naming it T sub n. So this system here, this generic system, is a PIDTN. Let's look at how we can use this. We have a second order system with a PID controller. What's the shorthand designation for this system? Well, it's a PI-T2, PI because there's no D term, and then the T2 indicates that it's a second order system on the left-hand side of the ODE. Let's write its ODE. So from this very brief shorthand here, we can write out this entire ODE. Notice that we have a second order ODE in XO. On the left-hand side, there's a second order derivative of XO. On the right-hand side, we have the P term, the proportional contribution, the integral contribution, but there's no derivative contribution. Now, another thing that we can do with this is that we can write the transfer function for the system, and this is actually fairly simple to derive from the ODE. you have to convert it into the Laplace domain. That's why we have these capitals here rather than small letters. So we assume that we have 0 initial conditions, and we convert this, and if we do that, I'm not going to go into that here because it's covered in other videos in this series, but what we wind up with is we have the output over the input, and so basically we're going to have XO on this side times a bunch of things. Actually, it's times this stuff in the denominator here, and then we're going to have XI times the Laplace transform versions of the proportional part and the integral part, and that's what we have here. And then if we simplify a little bit by multiplying the top and the bottom by s, we get this, and we get the s on the bottom here. So the transfer function for this system, once it's been simplified, is what we see right here. Notice what happens with the integral controller here is we wind up with a 0 in the numerator of the transfer function. Let's look at another example. This is actually a simpler example. We have a first order system that is P-only controller, and that's actually a quite common system defined in industry. So what's the shorthand designation for this system? Well, it's P. There's no I part, there's no D part, and since it's a first order system, it's just T sub 1. Right, it's ODE, so from that simple little shorthand version, we can write the ODE. First order on the left-hand side, NXO, and on the right-hand side, we only have the P part of the controller. We don't have the D part of the controller or the I part of the controller. Now, what can be seen actually from this example, and the reason that I used it is the reason we have T's as the coefficients on the left-hand side of the equation is that they're related to the speed of the system. And actually for this first order system here, T1 is what's called a time constant of the system. And you can look at another video in the series on first order step responses, and it goes into more detail about what that means. Now we'll write the transfer function. We do it exactly the same way. You take the Laplace transform of the left-hand side and the right-hand side, and then you form this ratio here of output over input. And if you get that, we get what we know as the first order or a transfer function for a standard first order system with the steady state gain on the top and the time constant as the coefficient of the S term on the bottom. Let's look at the chart again, well, let's just do it. Notice we have here, you have to look really with a magnifying glass almost, we have XA equals KP times XE. The A and the E are the German versions of I and O. So A is Ausgang, and that's output, which we would expect to see on the left-hand side. And on the right-hand side, the E is our I, Eingang, so that's the input. And this is really a very simple system. We don't have any derivatives on the left-hand side, so this is really a T0 system. This would be a PT0. But apparently, when we have no derivatives, we just leave the T0 off, and so the shorthand notation for this system here is just P. We're only talking about the first 3 columns in this video here, and so you can go through here and look at these, and then look in this Übertragungsfunction, that's the transfer function, and from the ODE be able to derive the transfer functions of each one of these systems here. The 4th column is actually the step response of the system, and I'll maybe talk about this, well, I have talked about it some in the, I have 2 videos, one about the response of the step response of a first order system and the step response of a second order system. But actually the step responses of all these different systems are shown in this Übertragungsfunktion. Then we have in the 5th column the Ortskurve, which is the Nyquist diagram, it's called in English. That's important for stability, and I may actually produce videos on that in the future, but so far I don't cover that. And then Bode plots are columns 6 and 7. A Bode plot is actually a coordinated pair of plots one that has the ratio of amplitudes of the input to the output, and the second plot is the phase difference between the input and the output. It's covered. That will be covered elsewhere in this series. And then actually what we have in column 8 is the pole zero plot of each one of these systems. And this is the start for the root locus of the system, also covered in, or it will be covered in other videos in this series. And then in the last column are technical, practical examples of each one of these different systems. You can download the chart if you like. I'll give a link in the description below, and you can click on that link and download the chart for yourself. It's a 11 by 17 chart, so you might, if you want to print it out, you'll need to have access to a printer that can print out a big version of that chart. And then I may come back and reference further videos in this series on this, or reference this chart in further videos on this series. And as always, thanks for watching, and I hope to have you as a viewer in future videos in this series.